Okay, here we go. This is chapter 25, Nuclear Chemistry, and hopefully this is clear enough for you guys. If you need me to, for any questions, you can get me at cusd.com. That's my email address. So please don't hesitate to write me if you guys have any questions about it. I just lost half the page there, didn't I? All right. There we go. Okay, so we're going to start with Henri Becquerel, who discovered natural radioactivity, which is the emissions of particles from the nucleus in 1896 from uranium salts. Now, this is 1896, and this is what the dude looked like back in 1896. How awesome is that facial hair? With all flying out of the sides, and he had to have been growing this for years since he was young, and then he's parting the beard. Way too cool. Okay, so he discovered the emissions of particles from the nucleus in 1896 from uranium salts. He caused, these salts caused photographic plates to become fogged without any sunlight and without any moisture. He just put them in a drawer and left them there and forgot about it. And then he took them out, and on a whim, he developed the photographic film, and there, lo and behold, there was a dot where the uranium salts was sitting on top of the film. And something had to have done that. Some kind of energy source had to have caused the film to become exposed, because they were in the dark the whole time. Well, Marie and Pierre Curie, who are these guys, okay, they are actually on they were on French money, the 500 franc note for their experiments with radioactivity, but they've since, France has since gone to the euro, so that currency no longer exists. They were husband and wife team that were two of Becquerel's associates, and they isolated and purified two new highly radioactive elements called radium and polonium. Radium because it was radioactive, and polonium after Marie Curie's native Poland. Okay, she named the process where materials gave off rays, and she called it radioactivity. She won two Nobel Prizes for this. One was in physics, the other was in chemistry, and she won another sort of prize, an unfortunate prize, as she is most certainly the first person to die from radiation poisoning, as her leukemia, the leukemia she caught, is almost absolutely stemming from her work with radioactive elements, not knowing what they would do to her. Okay, so, and she worked with these things called radioisotopes. So, those are the nuclei of unstable isotopes that gain stability by the emission of radioactive particles. And this technically is the definition of radioactivity. Is the emission of radioactive particles and trying to gain stability. Now, there are three main types of radiation that are emitted from unstable nuclei. There's alpha, with the Greek symbol alpha right there. There's beta, with the Greek letter beta, and gamma, with the funny looking Y down there. Okay, this is actually the Greek. That is the Greek gamma. Ernest Rutherford, remember him? He discovered two of the particles by radioactive elements, emitted by radioactive elements. He discovered the alpha and beta particles. Okay, he named them alpha and beta because he found the alpha first and the beta second. Okay, all of the emissions come from the nucleus. Now, there should be a warning sign going. Oh, actually, you don't know what a beta particle is yet, so you shouldn't really have the warning sign going off yet. Alpha particle. The alpha particle is the high-speed helium nucleus, if you remember from Chapter 4. It is composed of 2 protons and 2 neutrons, with a +2 charge emitted from an unstable nucleus. Now, it has not always been helium. Helium did not exist inside another nucleus. It just happens that it's 2 protons and neutrons that are shot out of the nucleus with a whole lot of energy, and if they were to become an atom and they were to take the electrons away from something else, they would become a helium atom. So that's why we call it a high-speed helium nucleus. It really is just 2 protons and 2 neutrons released from an unstable nucleus. There are a number of symbols for it. There's alpha. There's He2+, which just means it's the helium ion. Or there's the 4,2He, where the 4 is the mass number, 2 is the atomic number, and He is, well, it's the element symbol. Okay, they're big. They are heavier than all the other particles, and so they have low penetration. They don't go very far into your skin, and they are stopped by your paper and or clothing. Okay, they're stopped by paper and or clothing. So if you go near an alpha emission source, just by wearing your clothes, you're protecting your body. However, there are other forms of radiation that are more penetrative than an alpha particle. When a nucleus undergoes alpha decay, the new particle has a mass that is 4, has a mass number that is 4 less than where it started, and an atomic number that is 2 less than where it started. So, for example, uranium-238 right here has a mass number of 238 and an atomic number of 92. And so remember that mass number actually equals the number of protons plus neutrons, right? And where's my number sign? There you are. Okay, so the mass number equals the number of protons plus the number of neutrons, and the atomic number equals the number of protons. Okay, so over here in our equation, this 238 stands as our mass number and 92 is our atomic number. So the total number of protons that are involved here are 146 with another 92 protons. Collectively, these guys are called what? Oh, somebody got it, I hope. It's called a nucleon. Together, protons and neutrons are called nucleons. So anyways, a 238 will decay, and it will drop out, it will shoot out an alpha particle, okay, which will leave behind, so here's the alpha particle, and it will leave behind the rest of the nucleus, which is going to be the 238 minus the 4 from the helium nucleus, okay, which gives you 234, and at the same time, it's 92 protons that are losing 2 protons, leaving you with 90. So uranium actually becomes a new element because it loses 2 protons. And the new element becomes thorium-234. Now, a beta particle is a similar process, except instead of a helium nucleus, it is a high-speed electron. And this is that point where I'm hoping some of you guys have some sirens going off, that if this is a high-speed electron, then what is that doing coming from the nucleus? Because, well, the electrons don't come from the nucleus. Electrons come from around the nucleus. That's true. Electrons come from around the nucleus. However, in this case, it is produced from the conversion of a neutron into a proton. Okay, those are the symbols. There's a B for beta. There's a 0, -1 beta. This is getting kind of funky here. Okay. Or there's a 0, -1 E- for an electron. Okay, so let's see what the equation looks like when something gives up a beta particle. Alright, now a beta particle, when it travels, it has a medium penetration. It will go through your clothes and through paper. but it'll get stopped by, say, aluminum foil or some cardboard or thin wood or something like that. Some good dense cardboard. It travels really fast, about 0.9 the speed of light, 9/10 of the speed of light. So quite fast. And it has its own equation. The new particle is going to have the same mass, because if you remember, it was 0, -1. Let's see if I can do this without totally butchering it. It was a 0, 0, -1. Oh, that's ugly. Okay, so that winds up being a 0, -1 electron and a -1 charge. Okay, and so up here there's no mass number. The mass number is actually 0 because the mass doesn't change. Electrons are so small that it doesn't affect the mass of anything that it's around. However, because it has a charge, it is going to affect the atomic number. And this is the interesting thing. What actually happens is that one of the neutrons, for example, in carbon-14, okay, this is one of the things that undergoes beta decay, carbon-14 will turn into nitrogen-14. Okay, but look at the atomic numbers. We'll start off with 6. It actually increases. It goes from a neutron. There's a neutron that turns into a proton. Okay, when the neutron turns into the proton, it has an atomic number of 0 before. Then it kicks out the electron, which is like subtracting a negative. Okay, which actually turns that neutron, instead of being a 0, it turns it into a +1 for its atomic number. And that's how this carbon goes from carbon-14 to nitrogen-14 by turning a neutron into a proton. Okay, now, all of the elements in the universe, so we're going to pause, or we're not going to pause here, we're going to stop on those for a second. All of the elements in the universe come from either the fusion products of a star, so hydrogen fuses into helium, 2 helium fuse into 4, what is that? Beryllium. And then the hydrogen and helium fuse into lithium. And so all through about, maybe about number 20, element number 20, it all gets made in the normal process of a star. But anything higher than atomic number 20 requires a supernova. It requires a star to explode. And with such energies that it can cram all of those protons and all of those neutrons into a uranium nucleus, for example, or an iron nucleus, or a gold nucleus. Okay, and so it must take the extreme pressures of that supernova in order to make all of the heavier elements. And so, as the Crosby, Stills and Nash song used to go, "We are stardust." It's true. We all come from stars. All of our matter comes from stars and exploding stars and stars that have shed off their matter and have come into existence and died and given off their stuff. We all come from stars because that is how our elements get made. Okay. And the various elements get made because they make a whole lot of heavy ones when the star explodes, and then they start decaying, and some of them happen really fast. And they give off these particles, hoping to reach a more stable nucleus. And that's how we get all of the isotopes that we have today. And so an example of one is, back to the notes, a U-238 decay series. It requires a large series of alpha and beta decays in order for a radioactive substance, this U-238, to become stable. Okay, and it becomes lead-206. So, what happens if uranium-238 undergoes the following decays? And what is the final stable isotope? So here's what we have to go through. over here, we're going to start with, see if I can draw this well. Okay, so we're going to start with 23892U, and then it undergoes an alpha decay, which means it's going to lose 4 and lose 2 here to make the next step, whatever it is. And then it's going to undergo a beta decay, and then it's going to go another beta decay, and then it's going to go an alpha, and so on and so on. Now, there is an easier way of doing this than doing it one step each way. Now, I'm going to have you do that because I'm going to have you do that down here. But the easiest way of figuring out the final answer is each time you go through an alpha, it's a -4 at mass and a -2 atomic number. And each time you go through a beta decay, the mass doesn't change. You ignore the mass, but the atomic number goes up 1. So, it's going to go through 1 alpha, 2 alphas, 3, 4, 5, 6, 7, 8 alphas. Well, that 8 alphas is going to be ugly. It's going to be 8 times 4 equals 32 for our mass number, and then it's going to be 8 times, I'm just going to leave it, then it's going to be 8 times 2 for our atomic number change. But we can't just leave that alone. So it's going to be 8 times 2 equals 16. Okay. However, we also have 1, 2, 3, 4, 5, 6 beta decays. So we're also going to get a 6 times -1 equals -6 for our atomic number also. And both of these are for our atomic numbers. So you're going to take the 16 and add to the -6, and you're going to wind up with 10. And so what eventually happens is the mass number decreases by 32, and the atomic number decreases by 10. Okay, and you're going to wind up with 238 minus 32 is 206. And 92 minus 10 is 82, which is back to our lead over here. Okay. I'm sure you'll have questions on that, so we'll do another one another time. Now, gamma particles gamma particles are electromagnetic waves with a wavelength that is shorter than X-rays. Their symbols include that Y again, the funny Y, or the 00 gamma. Okay, and here's a funny poster with this. Okay, so everybody can see it. Let's spread this out here. Okay, so this is illustrating all the different kinds of waves that are out there. There's power and telephone waves. There's the human wave, which this isn't that far off. They've discovered that the human wave, you know, if you sit at Bulldog Stadium and you watch the wave go all the way around and then it dives in the red seats. Yeah, so that actually counts as a wave. Yeah, all kinds of stuff. CIA is listening here, ham radios, not so ham radio, cell phone cancer rays, gravity's up here, aliens are in here, SETI, potato waves, blog arrays, other sinister Google projects over here. This is just a fun poster. However, it does illustrate very well that all of our visible light right here exists in this very, very small part, and this is all part of the electromagnetic spectrum. Oh, what happened to my picture here? We're going to make that go away. Okay, so back to gamma rays. They're electromagnetic waves. These are the symbol. They are the highest penetrating particles. They are stopped by lead and only partially shielded by concrete. Okay? They are particles. They are a particle of light, which is an electromagnetic particle that travels at the speed of light. Okay? It travels at the speed of light. And so here's how it penetrates. Okay? Alpha particles will stop at the skin, okay, or clothing. Beta particles will pass through our skin, but they'll stop with this sheet with some aluminum foil. Gamma particles will go through our skin and through our aluminum foil, but they will stop with the layer of lead. They'll actually partially penetrate concrete, depending upon the thickness of the concrete. Neutrons go all through all of it. They're even more penetrating than gamma rays. The mass number and atomic number for gamma rays is 0, and no new particles are formed from gamma radiation. They usually accompany an alpha and beta and other forms of radiation. Gamma particles are the nucleus's way of getting rid of nervous energy. Nuclei will actually vibrate, and they'll sit there and they'll jiggle and jiggle, particularly if they're unstable. And in order for them to relieve some of the tension, they shoot out a gamma particle, and that relaxes them a little bit and allows the nucleus to settle down. Okay, it is the most damaging form of radiation because it passes right through the body and it'll hit your DNA and it changes your chemical bonding within your DNA. And when that happens, we get mutations. And mutations, no, you do not turn into superheroes like X-Men or the Avengers or whatever they're looking for. Or what, alphas is another way of, is like the modern day X-Men. It doesn't do that. It usually, well, it'll kill the cells, or it kills whatever cell is affected by the DNA that's been mutated. Not a good stuff. There are no nuclear equations for gamma rays. Okay, and the deflection of particles, or the stoppage of particles, is dependent upon their mass and the charge of the particles. So let's take a look at this guy. Where's my click? There we go. Okay, so you have radioactive source inside of a lead block, and you have an aligning slot that makes all of the particles coming through it and make a flat line. Then you pass it through an electric field. Well, this here, if I can only make this a little bigger, you get particles that are going to bend towards the negative, particles that are going to bend towards the positive, and particles that aren't going to bend at all. Well, what are the things that are going to bend towards the negative? It'll be the positive particles, which are the alphas, so they'll bend here. Then you have ones that are going to bend away from the negative or towards the positive, and those are the betas because they're negative. And notice that it actually bends a little bit more than the alpha, if you can see that. Then you have gamma rays, which have no charge whatsoever, and so they're not going to be affected at all. They'll just pass right through an electric field. Which brings us to nuclear transformations. Well, here's the question I asked you guys when we were talking about the structure of the atom. Why is it that the nucleus stays together? Why doesn't the nucleus fall apart if it's composed of positive forces and like charges repel? Well, the strong nuclear force, which I gave you guys earlier, is the force that bonds the nucleus together. I'm sorry, I should say binds the nucleus together. I make that mistake every year. It binds the nucleus together. Okay, and it is much stronger than the repulsive forces in between the protons. Now, this nuclear stability is dependent upon the stable ratios of protons to neutrons. There are more than 1,500 nuclear isotopes that we know. However, only 264 of them are actually stable and don't decay with time. Now, there's certain trends when it comes to stable nuclei. The first elements, elements 1 through 20, are most stable with a 1-to-1 ratio. Once you start increasing after 20 protons, the ratio gradually increases from 1.1 to 1 to 1.5, or a 2 to 3 ratio, 2 protons to every 3 neutrons. Okay, and that chart looks like this. Where we have a few Okay, so this right here is our band of stability. That's what we call this right here. And these are all of the known stable isotopes. Then we have the ones around it, which are the known unstable isotopes. And then there's the curious blue cloud, which is out here. And these are the unknown unstable isotopes that theoretically they exist, that they could possibly exist, but they're not long enough for us to really study them. And we're pretty darn sure that they will be unstable because they're not very close to this line. All of the stable isotopes are pretty close to this line. Notice how from about here to here, from 1 to 20, these are all stable. It's a 1-to-1 ratio. And then it starts to level out ever so slightly to become a 3 neutron to 2 proton ratio. Now, somewhere out over here is supposed to be an island of stability. My brother tells me that if we get the right numbers of protons and neutrons, they can actually find a region of atomic numbers that would be super dense but also relatively stable. We might actually be able to hold on to them for a while. So that would be really cool. Okay, so we have examples of stable isotopes. The ones we see most of the time, 12 carbon 12, nitrogen 14, oxygen 16. Those are 1-to-1 ratios. Okay, then we have others like 190 to 76 and 280. Those are 1 to 1.5, and notice that their atomic numbers are significantly larger. Okay, these are the stable isotopes of osmium and mercury. Okay, so notice that for every 2 protons, there would be 3 neutrons. So half of that would be 38, times 3 is 114. Half of 80 is 40. 40 times 3 is 120. So that's a 3 to 2 ratio between osmium and mercury. Now, where do our processes occur? If we have too many neutrons, this results in an emission converting a neutron into a proton. Okay, if we have too few neutrons, this results either in what's called an electron capture, okay, or a positron emission that results in the conversion of a proton into a neutron. So these can actually be reversed processes. Okay, and all nuclei with an atomic number greater than 83 are radioactive. It just happens. There is nothing, from 83 on up, you're going to be radioactive, and they are relatively unstable. Whenever we find an atom that's like that, it has the possibility of falling apart. Okay. And most of them are going to emit alpha particles to reduce the overall numbers of particles in the nucleus. Okay, on the next page, we introduce half-life. And no, we are not talking about the video game starring the ruggedly handsome but silent Gordon Freeman, who I, of course, am rumored to look like when I have my goatee. The definition of half-life is this. The definition of half-life is the time required for 1/2 of the nuclei of a radioisotope to decay to its product. The symbol for this is T1/2. Okay, Half-lives can be as short as a fraction of a second to as long as billions of years. The shorter the half-life, the more unstable the nucleus. The longer the half-life, the more stable the nucleus. So the longer the half-life, the less likely it is for any given instant to result in the decay of one of our nuclei. Because remember, nuclei, if they decay, they change their atomic numbers and they turn into something else. And so they aren't that thing anymore. They're something else. And so the longer they stick around, the more stable they are. Okay, so here are the calculations. Here are some examples. First example, we want to calculate the time it takes for 2 grams of carbon-14 to decay down to 0.125 grams of undecayed carbon. The half-life of carbon-14 is 5,730 years. So, how long is it going to take for carbon-14, 2 grams of it, to cut itself in half until it reaches 0.125 grams? Well, in the first 5,000 plus years, these 2 grams of carbon-14, okay, randomly, some of these elements, or some of these atoms, are going to decay into nitrogen-14, And so that's going to happen after 5,000 years, and you'll have 1 gram left. And after another 5,700 years, instead of 1 gram, you're going to have half as many. You're going to be down to half a gram. And this has a lot to do with probability. So if you have twice as many things, and you know that over 5,730 years, any one of them has a 50% chance of not being there after that time, then what you're going to have after that time is 1/2 of what you started to begin with, because there's a 50% chance of that atom of decaying. Now, then you sit there again, you have fewer atoms, and so you'll have fewer atoms that have the chance to decay. And this keeps going. So after 5 grams, it's going to go to 0.25 grams, and after that, it's going to go to 1.125 grams. And that would be 1, 2, 3, 4 decays. Okay, so therefore, it's going to require 1, 2, 3, 4 half-lives to decay the carbon-14 from 2 grams to 0.125 grams. Those 4 half-lives require 5,730 years, and so this is going to take 22,000 years, 23,000 years, for 2 grams to decay all the way down to 0.125 grams. Okay, the next example is radon. What percentage of radon remains undecayed after 19 days if the half-life of radon is 3.8 days? Well, after 19 days, when you start, how much radon do you have? Well, when you start with anything, you're always going to have 100% of what you start with. So we're going to start at 100. Start with 100%. But it goes for 19 days. 19 days divided into 3.8 day intervals winds up being 5 half-lives. You follow that? That if we're going to decay for 19 days, and every 3.8 we have half of our radon, then how many half-lives is that going to be? And that's 19 divided by 3.8 to give us 5 half-lives. Okay, and so we're going to start with, and if we're going to go through 5 half-lives, we have to do 5 cuttings in half of our half-life. So there's 100%, that's 2 cuts, 3 cuts, 4 cuts, 4 cuts, and 5 cuts. And so we would wind up with 3.125% of radon-22 after 19 days. Okay. Finally, what is the half-life of a radioisotope if it takes 2 minutes and 12 seconds to cause 8 grams of it to decay to 0.125 grams of the original sample? Okay, this is going to be pretty cool. If it goes from 8 grams to 0.125 grams, how many cuts does it make? Well, if we start at 8, we cut in half, that's 1 cut, that's 4. Then we do another cut to 2, and another cut to 1, so that's 3 cups, right? 3 cuts, right? 8 to 4 to 2 to 1. But we're not there, we're going to go to 0.125, so we go one more to 0.5 grams, then to 0.25 grams, and then, bam, we hit 0.125 grams. To do this, it takes a total of 2 minutes and 12 seconds. So there's 1, 2, 3, 4, 5, 6 half-lives in 2 minutes and 12 seconds. So we're going to take our 2 minutes and 12 seconds, which is really 132 seconds. Okay, our half-life is 132 seconds divided by the number of divisions that it's done in that time, which winds up being 22 seconds. And so the half-life of radon, or the half-life of this isotope, would be 22 seconds. And this could actually be something we could use to characterize what isotope it is, because most isotopes have their own unique half-life. And this brings us to transmutation reactions. Okay, so transmutation reaction is the conversion of an atom of one element into the atom of another element. Transmutations can occur in 2 different ways. One is through radioactive decay, and 2, by nuclear bombardment, where we actually shoot particles at the nucleus hard enough for the nucleus to absorb it. Okay, so we've been over radioactive decay. Let's talk about nuclear bombardment. Nuclear bombardment accelerates a subatomic particle to a relativistic energy, meaning it's traveling almost at the speed of light. And then it collides and combines with the nucleus of an atom. Okay, and when that happens, so subatomic particles accelerating, we do it to neutrons, we do it to protons, alpha particles, etc. The particle accelerators, like those at the Fermilab, okay, and Fermilab is, where are you? Okay, this is Fermilab, right here. And it sends some things one way, and it goes this way, and it sends another one that way. And so they go into each other, and they go kablam right here, splooey! And so they send them in opposite direction. They slam them into each other, and they make pictures like this. Okay, which is really cool. And let's move this to the top layer. Kablooey! And there's really cool stuff happening here, and all kinds of stuff spinning out of control. And this is under a really high magnetic field, and so you get all kinds of really tight spins and other things popping into existence and leaving, and it's all wicked stuff. Okay. Okay, and that's what happens at Fermilab. Okay. Or, which is in Batavia, Illinois, there's the Lawrence Livermore Lab, okay, which is in Livermore, California, which happens to have the world's largest laser, and this is it. It's kind of tough to see, but it's okay. It shoots a hold on a second. Yeah, this one. Okay. So it shoots down a laser. Each one of these boxes, you can kind of see these rails. Each long box, contains a laser that is about the size of the smart board you have in front of you. And there are 192 of them, and they travel back and forth in this room, and it's huge, it's huge laser. And all these lasers get divided up into now mind you, that's the cross section. is the size of the smartboard, and they all wind up getting bounced around and focused into this chamber here. I've actually been there. Gets focused into this chamber here, and right about there, top of where this guy's standing, is something that's going to be the size of an eraser tip. Okay, so see all these holes? They're all these holes are focusing the lasers onto this thing. It's about the size of an eraser tip. It's right here. And all of these lasers focus inside this chamber to convert this little ball of hydrogen into helium. And it's a laser-based fusion reactor. And we're hoping that we can do it with enough energy coming out to overcome the amount of energy we put into it. Because as soon as we can start doing that, then we have achieved an energy efficient or an energy positive fusion reaction. And that's the ball game, folks. That is really going to solve all of the world's ills, because all of a sudden we'd be on the verge of a supply of limitless energy. Okay, and there's another one in CERN, and this is the Large Hadron Collider, the LHC. This is the granddaddy of them all. Okay, and this is it here. And this bad boy, again, let's put this at the top later. Okay, here's the large. It has its own airstrip. Okay, you can see all of the towns here. Okay, here's the Atlas and Alice and the LHC Collider. Okay, and right here is, right there in the distance, right there, is this building here. Okay, so it's hidden right in there. Okay, this is the entrance to CERN. This was built into the side of a mountain. It had to be built underneath the curvature of the Earth. And this is about 25 miles across. Okay, it's huge. I think it's 25 miles around, and it's about 8 miles across to go there. It's ginormous. This is Lake Geneva in the back, and this is Mont Blanc, the Switzerland, the Swiss Alp up there. So those are the Swiss Alps. Here's Lake Geneva. This is in Switzerland. It does cross into France a little bit. I believe France is down here. And there's a little mountain range. I believe that is the frontier. So anyways, that's the Large Hadron Collider. That's where it is. And that's how freaking huge it is. And that's where we do all the really cool science lately. Okay. Now, for example, they are able to bombard an aluminum-27 nucleus with an alpha particle. And so the 2713 aluminum gets hit with a 4-2 alpha particle, and it becomes 3014 silicon. Now, we're missing something here, because we have 27 nucleons here, plus 4 nucleons, should be a total of 31, but there's only 30. And there's 13 protons here, and 2 protons here, which should be 15, so we're missing a 1-1 particle. Now, what particle do you think would have a symbol of 1, 1? It's got 1 atomic mass number and 1 atomic number. Well, anything with an atomic number has got to be a proton. Okay, and so that creates a silicon nucleus, and it emits a proton. Now, it so happens that atomic number 1 is hydrogen, and so this actually emits a hydrogen nucleus. Now, there are extreme ways of bombarding nuclei and doing stuff with nuclei, and they are fission and fusion, and these are the sources for a lot of our energy. Okay, nuclear fission. Atomic fission involves the bombardment of 2 fissionable isotopes, either uranium-235 or plutonium-239 with a neutron. We hit it with a neutron. The resulting nuclei are so unstable that they break apart into two smaller daughter nuclei, releasing more high-speed neutrons. Okay, and the mnemonic for this is fission is division. Okay, and this brings us to, this is the fission equation for bombarding a uranium-235 nucleus. We hit it with a neutron, okay, and then it hits U-235 nucleus, turns it into a U-236 nucleus, but just for a little bit, because there's a lot of energy there, and it's not very stable at all. So then it turns into its daughter nuclei, which would be krypton and barium. Now if you look again, krypton is sitting here with 91 nucleons, and barium is sitting there with 142 nucleons, and so that's a total of 233 nucleons. We have 236 to account for. Now 36 and 56, that's 92, so we've got all of our protons, but we're still missing 3 nucleons that are not protons, and so they must be neutrons. And so they actually get released individually with a little bit of energy. Okay, this then creates a chain reaction, because the fissioning process starts with one neutron causing one atom to break apart. And when it splits, it gives these 3 neutrons, and they send those 3 neutrons to go hit 3 more uraniums. Okay, which is going to split and give off, each one of those is going to split and give off 3 more neutrons, which is going to go hit 3 more uraniums, so now we're up to 9 nuclei. And then each one of those 9 gives off 3 to hit 3 more nuclei, going up to 27. And so on, 81, 241, 2723. Those aren't right. That should be, oh, I should correct this. Okay, those numbers are better. So, it's 1 to 3 to 9, 27 to 81, and then those put off 3 to make 243, and those put off 3 to make 729, and so on and so on, with trillions and trillions of reactions in less than a second. Okay, so go see figure 2510. Okay, because that's going to show you what that looks like. Now, when atoms split, a tiny amount of mass is destroyed. It's about 0.1%. However, that gets converted into energy based on E equals mc squared. Yes, that E equals mc squared. Einstein's mass to energy equality. So E equals energy created, measured in joules. M is the mass defect, or it's the mass lost, measured in kilograms. Okay, and C is the speed of light, which is about 3 times 10 to the 8th meters per second. Well, if you square C, that makes 10 to the 16th, and that becomes a really big number really fast. So even if the amount of mass is really small, the energy is huge. So it brings us to, like we said, C squared is a really big constant, 9 times 10 to the 16th meters squared per second squared. You're not going to be expected to know how much energy is released, because you don't even know what the energy is, so I'm not going to require that of you guys. However, recognize this, that an average atomic bomb might have about a kilogram of U-235 in it. Just a kilogram, about 2.5 pounds, or 2.25 pounds. When 1 gram of U-235 is destroyed, it's the size of a BB, and so this loses about 1 gram of U-235 and converted into energy. Okay, if the 1 kilogram fission bomb releases the same amount of energy as 20 kilotons of dynamite. 20,000 tons of dynamite. Ridiculous amount of energy, all concentrated in one place. Okay, now fission is also used in nuclear reactors, and you need to know this. Okay, there are some advantages to nuclear energy. Okay, there's lots of energy produced frequently with minimal effects on the environment. Okay, it is usually reliable. It is usually very reliable. Okay, and it doesn't cause air or water pollution like use of fossil fuels. And there are many American-designed safeguards. However, some of them you just can't control for, like, say, having a tsunami and an earthquake happen at the same time. Nuclear reactors, nothing is designed to withstand that. Then there are some disadvantages also. There's a limited amount of fuel, and the plutonium U-239 breeder reactors are not as safe as U-235. The products of the fission reaction have long half-lives, and they're very radioactive. And so they have to be stored, so we produce a lot of it, okay, and they have long half-lives, so we have to store them for a very long time. And storage for something like that is very expensive. And nuclear waste could be stolen and converted into plutonium-based bombs, which also is a bad thing. Okay, so the waste places are heavily guarded. Okay, which brings us to the answer, which is nuclear fusion. Fusion is the bringing together, or the combining of small nuclei to produce a larger one. For example, two hydrogen isotopes, hydrogen-2 and hydrogen-3, also known as deuterium and tritium. Okay, they will combine to make helium, which is utterly harmless. You all know that because you can breathe it and your voice starts sounding like this. Okay, and it gives us a neutron and some energy. Matter is destroyed, just like in fission, and converted into energy from E equals mc squared. However, fusion is more efficient than fission because 0.5% is converted into energy as opposed to 0.1%. So it's 5 times as efficient as fission. Fusion is also what powers the sun. We have a constant fusion reaction lighting our sky, providing 100% of our energy. Of all the energy that we produce on the planet, all of it comes from the sun. You can trace all of it back to the sun. From wind energy, solar energy, to nuclear energy, all of it can be traced back to stars. And fusion reactions are the answer to our energy demands for the future. There really is no other option. We have to go through fusion because we have a limitless supply of the material needed to do it, to do fusion, and the amount of energy we get out of it would make the economic impact minuscule. Okay, which brings us to nuclear bombs. Atomic bombs are fission bombs using U-235 and plutonium-239. So the isotopes of uranium and plutonium. In order to make an atomic bomb, we had the Manhattan Project, which was a top-secret government project to design and build the atomic bomb under the football field at the University of Chicago. Okay, which led to the Trinity Project, in which three bombs were made. There was a demonstration in Alamogordo, New Mexico, and then the 2 that were dropped. The other 2 that were actually dropped in anger, and they were the only 2 that have ever been dropped as attacking weapons against an opposing force. The atomic bombs reach temperatures above 10 million degrees Celsius, and they release all forms of radiation, and they are a fission reaction that has gone horribly out of control. Now, we of course like bigger and better bombs, and so we made fusion bombs, which are called thermonuclear bombs, or hydrogen bombs. They use an atomic bomb, a fission reaction, to detonate the fusion bomb. That's how they get all the energy to make the fusion start. In 1951, we dropped the first hydrogen bomb. It was detonated in the South Pacific island of Bikini Atoll. Now, rumor has it that the Bikini Atoll was not actually an atoll until they dropped the bomb on it, and then it became an atoll. Again, someday I'll show you a picture when I get back to class. Some scientists thought it might ionize the atmosphere, which would, completely tear all of the compounds and all of the gases in the atmosphere and turn them into ions. Fortunately, that didn't happen. It was 1,000 times more powerful than the Hiroshima bomb, and it reached 100 million degrees Celsius. We put these suckers on top of ICBMs, which are called intercontinental ballistic missiles, and most of our nuclear warheads are hydrogen bombs, and the warheads on these things contain multiple bombs. So you launch one, you set it and forget it. You launch it, and it will attack 10 different targets. So just let them go from space, and they'll fly down, and they'll attack 10 different targets on their own. Okay, which brings us to radiation in your life. We have 3 basic devices for detecting radiation. There's a Geiger counter, there's a scintillation counter, and film badges. This is what a film badge looks like. Right here. Okay, so if you look at the film badge, there's a monitoring film in here, and look at the kind of filter that it has. It has an open filter, it has an aluminum filter, a copper filter, a plastic filter. Okay, what do you think is going to show through the open window? Well, it's the things that don't have a filter, and so that's going to be the alpha particles are going to show up through here. Okay, but if you have the plastic filter, well, that's going to see if you have some high energy alphas as opposed to just betas, but it's going to get stopped by the aluminum filter. Betas will get stopped by the aluminum filter. And so if you have markings here on the copper, now you're talking about neutrons and gamma radiation, and that's bad. If you've got exposure up there, now you really felt it. So the monitoring film, which goes all the way back to Becquerel, all the way at the beginning, they put photographic film there, so that when it gets detected and you enter radiation, you know exactly which type you have. Okay. And then finally, we actually use radiation. We use radioisotopes in medicine to detect various disorders. We detect it in the thyroid. It can also detect tumors and liver disorders in nuclear medicine. And people take radiation therapy and radioactive isotopes to go attack cancers in the body. And that's it. And I know that was a long one, but that's the entirety of Chapter 25. And fill out your notes, and I will see you on Monday if we actually get through all of it. Peace out. Word to your mother.